This video is about K-means clustering, which is a tool for data mining. Data mining uncovers hidden patterns and relationships in data through the application of data analytical techniques. There are two types of data mining: supervised and unsupervised data mining. Supervised data mining is the one whereby target variable is known. Target variable is also called as dependent variable in linear regression. In supervised data mining, target variable is known. We only want to predict its value. So for example, when we are conducting linear regression and we want to predict home prices, home price is the target variable, also called as dependent variable. In linear regression, we want to predict the value of home price using a set of predictors. For example, interest rate, size, location, and number of bedrooms. Similarly, if we want to make a prediction about aggravated assault or crime rate, that's a target variable. And we use a number of predictors to make a prediction about the value of aggravated assault or crime rate. In unsupervised data mining, there is no target variable. Indeed, it is irrelevant because we are not going to make a prediction. Our objective is pattern discovery, finding inherent structures within data. In this unsupervised data mining process, data points group themselves based on similarities. An example of application of unsupervised data mining is customer clustering, which is grouping customers by purchasing behavior. Here is a comparison of supervised and unsupervised data mining. In supervised mining, target variable, which is also called as dependent variable, is known. We only want to predict its value. So for example, when we are conducting linear regression, the purpose of linear regression is to make a prediction about home prices or crime rate. And in supervised mining, we tell the algorithm to use these inputs to predict the value of a known variable. On the other hand, in unsupervised data mining, target variable is unknown or is irrelevant because we are not going to make a prediction, because our objective is discovery. And an example of the tool used for this purpose is K-means clustering, which is used for customer segmentation. In unsupervised data mining, we tell the algorithm to explore the data to discover groups or patterns. K-means clustering, which is about grouping data points into clusters, is an unsupervised machine learning algorithm used to partition a data set into distinct, non-overlapping subgroups or clusters. For example, I applied K-means clustering to a data and that gave me these three clusters. Each cluster is represented by oval shape. So this is first cluster, second cluster, and third cluster. Here is an example. A vendor of chocolates wants to group chocolates into 3 to 4 clusters. So if we choose 3 clusters, K will become 3 based on their nutritional contents, calories, fats, proteins, and carbs. This will allow the vendor to strategically place the chocolates in vending machines in a way that appeals to different customer preferences. And based on this information, vendor can categorize customers into different categories such as health conscious buyers, indulgence seekers, and taste first consumers. One of the most effective approaches to determine these clusters is K-means clustering. This is the data on which I will apply K-means clustering. In this data, we have 5 columns. First column is about chocolate names. Second column is about calories. Third column is about fat contents in grams, protein, and carbohydrates. This is only a snapshot of data. Actual data has 45 entries or 45 rows or 45 chocolates. And our objective is to cluster these 45 chocolates into 3 clusters. I will do K-means clustering in RStudio. I will install this package using this code install.packages cluster. Cluster is the name of package that will be used. The next step is to load that package, and for that purpose I will use this code library cluster, and that will load the package. In the third step, I want to import data. My data is in a CSV file and I want to import it into RStudio. I want to name this file as chocolate. You can use any other name. And for that purpose I will use this command read.csv file.choose and parentheses, and when I run this code it will open a new window so that I can choose my file. The next step is to attach this data. If you want to see how this data looks like, I will use this code view chocolate. Chocolate is the name of the file. I will run this code. It shows that this is our data. This data has 45 entries or 45 chocolates. There are 5 columns: name of chocolates, calories, fats, proteins, and carbohydrates. In this data, we do not need the first column because the first column is nominal variable. It is not numerical variable. R cannot use this data and we don't need it. We only need this numerical data. So therefore, I will specify that only use column number 2, 3, 4 and 5 and exclude column number 1 because it is nominal variable, not numerical variable. And for that purpose, I will use this command chocolate, which is the name of the file, and I will specify use 2 to 5, which means use column number 2, 3, 4 and 5, and whatever is the result, store it as chocolate. So this is the name of the object that will be storing the data from column number 2 to 5. In the next step, we want to scale this data. The reason I want to scale it is that because I want to make these data points comparable. The data about calories is in 3 digits. On the other hand, many values in fats and proteins are in single digit. So for example, 8 is single digit, 6, 9, 7, 3, 7. All these values are in single digit. Therefore, we need to make them comparable because k-means clustering uses Euclidean distance. And if these values are not comparable, k-means clustering will give incorrect results. So therefore, we need to make them comparable. And one means to make them comparable is to standardize them. And for that purpose, I will use this command scale chocolate. This code will provide standardized scores. And whatever is the result will be stored in this object, which is chocolate. Initially, all the values in this column were in 3 digits. But now all these values are comparable. This is an essential requirement for k-means clustering. The next step is to use set.seed1. This code is needed for reproducibility and consistency. If you want to make sure that you are getting the same results and you just want to make sure there is nothing wrong with the code, we use this code. The core code for k-means clustering is this one, PAM. PAM means partitioning around midioids, and this is the name of the file. K is equal to 3, which means I want to make 3 clusters. The results are stored in this variable k result, and if I run it, it gives me these results. So these are our 3 clusters. I'll be explaining them in more detail in a minute. And in the last step, I want to make a plot of these results. So I'll be using this code plot k results, and this is the title. If I run this command, it will make cluster plot, and you can see here there are 3 clusters, 1, 2 and 3. And if I run the same command one more time, it will convert the same plot into silhouette value. And if you run the same code one more time, it will revert to the original one. Here we have these 3 clusters, and this is about cluster assignment, which means first cluster comprises 17 points, second cluster also comprises 17 points, third cluster comprises 11 points. This is assignment of data points to each cluster. So these are 45 values because we have 45 chocolates or 45 data points. And this shows that the first data point in our file belongs to cluster 1. Similarly, this one, which is 5th value, 6th value, 7th value, and 8th data point also belong to first cluster. And then 14th, 15th also belong to first cluster. And then 25th and 26th also belong to first cluster, and then 35th, 36th, 37th, 38th and 39th data point also belong to first cluster, and the last 3, 43rd, 44th and 45th data point also belong to first cluster. As you can see here, this shows that first cluster comprises these data point 1, 5, 6, 7, 8, 14, 15 and so on. Similarly, cluster 2 comprises data point number 2, 3, 9, 10, 11, 12 and so on. And these data points constitute cluster number 3. If we go back to our data file And if we see what are the characteristics of these clusters, so for example, cluster number 1 comprises data point 1 and 5. So let's go back to data point number 1 and 5. And data point number 1 is this chocolate. Calories contents are very high, fat contents are also high, and carb contents are also very high. The same thing you can note in point number 5, whereby calorie contents are very high, fat contents are again very high compared to 7, 9 or 6. Protein contents are relatively low. Carb contents are also very high, that's 31. This means that our first cluster has high calories and more fat and carb contents. So therefore we say cluster 1 has high calories, high fat and high carbs, indulgent or high energy chocolates. Similarly for cluster 2, so cluster 2 for example comprises these data point 2, 3, 9, 10. So let's see what's point number 2. So point number 2 has relatively low calories, only 173 calories compared to 312. Fat contents are really low and carb contents are also low compared to 32. This means that our second cluster will contain chocolates that have low calories, low fats, low carbs. So we can say that second cluster has low calories and high proteins, and therefore we call it light low energy. And third cluster comprises these data point number 4, 21st, 22nd, 23rd and 24th and so on. These data points represent chocolates which have moderate calories, low fat, low protein and moderate carbs. In this table, this column represents clusters. So this is our first cluster, this is second cluster and this is third cluster. And the second column represents medioids. Medioids are actual data points that are representative of that cluster. So data point number 6 or row number 6 in our data represents first cluster. Similarly, 33rd row is the representative of second cluster and this number is representative of the third cluster. These values represent standardized scores. This is silhouette value plot. Silhouette value evaluates the quality of clusters. It measures how similar an object or data point is to its own cluster, which means cohesion, compared to other clusters, which means separation. Silhouette value ranges from -1 to +1, whereby +1 indicates that the object or data point is well matched to its own cluster and poorly matched to neighboring clusters, which is a good thing because it means there is a good fit, good cohesion, because data points are matching to their own cluster, and that's a good thing. 0 indicates that the object or data point is on or very close to the decision boundary between two clusters, and -1 indicates that the object or data point may have been assigned to the wrong cluster, which is not a good thing because the data point has been assigned to a wrong cluster. In this case, average silhouette width is 0.73, which is positive. It means strong clustering structure. The clusters are well separated and most data points are correctly assigned to their respective clusters, which is a good thing. High cohesion and separation, which is again a very good thing because it means that data points matching with other data points in the cluster and are clearly distinct from other clusters. Data points within the same cluster are closer to each other, high cohesion, and clusters are distinct and far apart from each other. And last thing is that it means good choice of K, which means decision to make 3 clusters is likely appropriate. Whenever we have some negative silhouette values, they appear here on extreme left side. But in this case, we don't see here any negative values, which mean that all data points are assigned to their clusters and it's a good model. Now this is time for reflection. In this technique, the R algorithm generated these 3 clusters. The only input that we provided was number of clusters. The underlying process was that the first step was initialization, which means specifying the number of clusters, which is k is equal to 3. In the second step, our algorithm assigns each data point to the nearest cluster based on Euclidean distance. And in the third step, it recalculates the medioids of each cluster based on the the mean of data points assigned to it. And this is an iterative process whereby data points are assigned until we get a good model. So for example, here you can see when it initially made a model, this model has this value 0.61, and then data points are assigned, and that improved the model, and that changed the value from 0.61 to 0.52. K-means clustering is used for customer segmentation based on purchasing behavior, which helps in enabling targeted marketing strategies. It also helps in anomaly detection, whereby it helps to identify outliers in data by grouping normal patterns and flagging points that fall outside the cluster. K-means clustering is also used for fraud detection. It groups financial transactions to detect unusual patterns indicative of fraudulent activity. Most of financial transactions, routine transactions, tend to form some cluster, but if there is a fraudulent activity that doesn't match with other, it will appear as an outlier and it will be flagged. And the last thing is that K-means clustering is also used for product recommendation. Cluster users with similar browsing or purchase histories to recommend relevant products.